गर्मी सवारी कितनी થઈ ગઈ पूरे गया होगा कोई
This is the most dramatic footage of a Boeing 787 in flight and on the ground. On June 12, 2025, a Boeing 787 Dreamliner crashed shortly after takeoff from Ahmedabad, India. But this wasn't the first time the Dreamliner faced trouble. In 2013, a 787 caught fire in a dramatic fashion during a test flight. Now, it seems like every new technology has its growing pains. The 787 is no exception. During the test flight, the plane was experiencing some sort of problem. The pilots were trying to troubleshoot the issue when suddenly the plane lost power and began to fall from the sky. Now, the cause of the crash is still under investigation, but early reports suggest that the plane may have been experiencing some sort of technical difficulty. This is a developing story. We will keep you updated as we learn more.
Are you worried about aviation safety after the recent Boeing 787 crash, exposing the critical errors that led to disaster, and what it means for the future of flight? On June 12, 2025, a Boeing 787 crashed shortly after takeoff from Ahmedabad, India. While details are still emerging, investigators have zeroed in on two key technical problems. First, the landing gear remained down during climb, causing dangerous drag. Second, the flaps retracted too early, reducing lift when the plane needed it most. These missteps likely contributed to the loss of control. While the 787 has faced past safety issues, including battery fires in 2013, ongoing scrutiny has pushed for stronger quality controls and better pilot training. Experts say advanced automation, clearer cockpit alerts, and real-time monitoring could help prevent similar incidents. Every crash is a lesson. As investigators work to uncover the full story, the goal remains clear: making air travel safer for everyone.
Animation video of flaps up, hand gear down in the Boeing aircraft.
Within 30 seconds to 2 minutes, during ascent, the aircraft suffered a sudden failure to gain altitude, possibly due to engine thrust issues, bird strikes, and incorrect takeoff configuration, landing gear with flaps still down. The aircraft crashed into a building, a medical college hostel. Out of the 242 souls on board India Flight AI171, only one lived. Now we'll show about Boeing 787 in detailed documentary.
Your local airport has more direct flights to distant lands than ever before, and the price of those tickets are cheaper than ever. Connecting flights are becoming rarer and rarer as this new breed of plane takes over. The plane at the forefront of this revolution? The 787 Dreamliner, a $30 billion bet on the future of the airline industry. Boeing sat at the poker table and pushed all their chips forward. An all-in bet on a radical new future. And it paid off. The 787 revolutionized not only how the airline industry operates, but how the future of planes will be designed and built. This is the breakdown of the 787's materials. By weight, 55% of the 787 is made from composite materials, like carbon fiber reinforced plastics, making it the first commercial airliner made primarily with this new age material. The 787 is rivaled only by the Airbus A350 XWB, introduced 4 years after the 787 in 2015. So, why are composite materials so desirable for the airline industry, and how has the 787 made the most of their advantages? Composite materials are made up of two or more materials. Take carbon reinforced plastics. They are composed of extremely strong carbon fibers bound together by a plastic resin. Carbon fiber, made up of thousands of tiny thin fibers of carbon, is incredibly strong in tension, up to 5 times stronger than steel and 1/5 of its weight. But these tiny fibers can't create a solid part by themselves. This is an image of a human hair beside a carbon fiber. The carbon fiber is the smaller one. And just like a human hair, they can bend and flex and separate very easily. So we need to first bind them together with a plastic resin to form a solid material. Otherwise, they just form a strong but flexible fabric. That flexibility as a fabric is exactly what makes composites so useful when creating the precise and elegant curves of a plane. With the right tooling and designers, composite components can be made into almost any shape imaginable. In the past, a disadvantage of making large aircraft components from composites was the time taken to manually lay up parts, where layers of carbon fiber and plastic resin had to be carefully constructed. It required skilled technicians and was inherently difficult to scale to the production quantities Boeing needed. To get around this, Boeing uses automated tape laying to produce massive aircraft sections. The 787's fuselage is created by wrapping a carbon fiber tape impregnated with a plastic resin around a rotating mold of the fuselage. This machine precisely controls the overlaps of the tape and the orientation of the fibers to ensure we are getting the most out of the carbon's tensile strength to resist the internal pressure loads and the longitudinal bending loads the fuselage will experience. One of the problems with this manufacturing method is that the part needs to be placed inside an oven to cure the resin. This hardens the plastic and creates a solid composite structure. Ovens the size of a wide-body jet airliner fuselage are not exactly common, and this is often the limiting factor on parts made this way, and requires massive upfront investment to build a customized oven large enough to fit the part. But the benefits are well worth it. The first and most obvious is the strength carbon fiber provides. Previous generation airliners are typically pressurized to an equivalent of 8,000 feet. That's the same height as Mount Olympus in Washington state. High enough that the lower pressure would reduce your oxygen intake and your stomach will bloat as the air inside is higher pressure than the outside. This is uncomfortable and exacerbates the effects of jet lag, but thanks to the 787's stronger fuselage, it can increase its internal air pressure to an equivalent of 6,000 feet, 25% lower in altitude and about 7.3% higher in pressure. That may not sound like a lot, but it goes a long way in making the journey more comfortable. And at the very least, the person next to you won't be farting as much. Less farting is always nice, but my favorite benefit of the stronger fuselage is the absolutely massive windows. This is the 787 window, and these are windows of some equivalent aluminium airliners. They are absolutely massive. In aircraft made primarily from aluminium, having holes this large in metal panels would result in the buildup of stress at the window boundaries, as the stress contours have to deviate around the window. This stress does not exceed the material's strength, but over repeated pressure cycles, tiny imperfections in the metal can grow into even larger cracks and eventually fail. Holes this large in an aluminium airliner would severely shorten the plane's flying career before it needed to be fixed or disposed of. Kind of like how cracks in McGregor's leg shortened his career. But it's not a problem for the 787 thanks to Composite's relative immunity to fatigue. You could kick Dustin Poirier's kneecap as many times as you like with carbon fiber shins. The carbon fiber construction provides plenty of benefits for the airline operators too, because the fuselage is just one massive part. Boeing was able to eliminate all joints and all the fasteners needed to join them together. Sections that used to be made up of 1,500 aluminium sheets riveted together using 40 to 50,000 fasteners are now just one massive carbon fiber section. Carbon fiber's strength to weight ratio already makes the fuselage lighter, but eliminating joints and fasteners makes it even lighter again. The reduced weight reduces fuel burn, but this fuselage is also incredibly aerodynamic because it doesn't have thousands of little bumps and ridges all over it from those joints and rivets. These surface imperfections make the plane's surface rough and cause it to disturb more airflow, increasing parasitic drag. Composite materials help reduce drag in other ways too. One of my favorite things about the 787 is its elegant wings. The main structural member of a wing is the wing spar. Its primary role is to resist the upwards bending force during flight. It's essentially just an I-beam, a shape optimized to resist bending loads. The wing spars of the 787 are constructed from carbon fiber composites, while the ribs, the structural members connecting the two spars and that support the wing skin, are machined out of solid aluminium plates. The structure the rear and forward wing spars form, with ribs running between, is called the wing box, and it forms the main load-bearing structure of the wing, while also being a literal box for fuel to sit inside. The carbon fiber composite spar provides the wing fantastic strength. Strength is quantified by the force required to completely fracture material, but carbon fiber composites have another important quality that makes them perfect for aircraft wings: their maximum elastic strain. There are two types of deformation: elastic and plastic deformation. Elastic means the material will snap back into its original shape after the load is removed, like an elastic band. Plastic means it will permanently deform and won't return to its original shape once the load is removed. Something we don't want to happen. This is permanent damage. Carbon fiber composites can deform further before they strike this plastic deformation zone at about 1.9%, while aircraft aluminium begins permanently deforming at less than 1%. That means we can bend carbon composites further before we need to worry about permanently deforming them, and that means we can make our wings super flexible. During flight, the wingtip of the 787 can move upwards by 3 meters. That sounds like a lot, but in order to get certified by the FAA, every plane needs to be able to handle 150% of the plane's absolute maximum expected load during flight for 3 seconds. And during that test, the 787's wing bent upwards by 7.6 meters. That's a great deal of bending, despite carbon fiber composites being stiffer than aluminium, meaning it takes more force to deform the same volume of material. But critically, 787 wings are not the same shape as their aluminium counterparts. This ability to withstand greater bending allowed engineers to make the 787's wings with a much higher aspect ratio. Aspect ratio is the ratio between the wing span and the mean chord, or wing width. A high aspect ratio would be a long skinny wing like a glider, while a low aspect ratio would be a delta wing of a fighter jet. A traditional airliner has an aspect ratio of about 9, like the 787's predecessor, the 777, but the 787 has a massive aspect ratio at 11. This is what causes the 787's wings to flex so much during flight. Composites are actually stiffer than aluminium, but their ability to withstand high deformation allowed the engineers at Boeing to create a much higher aspect ratio wing, a longer, narrower wing that would bend more. But this comes with some huge benefits. The planes with the highest aspect ratio are gliders. For an unpowered plane, the highest priority is minimizing energy lost to drag. This allows the glider to stay in the air for extended periods with no engine. These types of aircraft typically have aspect ratios greater than 30, and these aircraft have the lowest drag penalties as a result of vortex drag. This is the drag caused by air mixing from the high pressure zone under the wing with low pressure air above the wing, forming vortices at the wing tip. By spreading the area of the wing over a longer span, we minimize the pressure that drives this mixing at the wing tip, and thus minimize the energy lost to the vortices. Normally, higher aspect ratio wings have lower internal volumes. For an unpowered glider, this isn't an issue. But for a plane that needs that storage space for fuel, it is. Less storage volume for fuel means lower range, and one of the primary goals of the 787 is to be an efficient, long-range aircraft, capable of allowing airliners to open new routes that were once deemed impossible. Thankfully, modern planes like the 787 use a new kind of aerofoil, the supercritical aerofoil. Older aerofoils look something like this, a reasonably symmetric design with a sharp nose and gentle curves on the upper and lower surface, and this is a supercritical wing. The leading edge is blunter with a larger radius, the top is relatively flat, and the lower portion has this strange cusp at the back. This aerofoil has much more useful internal volume thanks to its blunt leading edge and larger thickness to chord ratio, helping solve our low internal volume problem associated with high aspect ratio wings. The supercritical wing was first tested by NASA on a modified TF-8A Crusader, and you can really see the similarities in design ethos between the experimental plane's sleek wings with the 787. But increased internal volume is not why NASA developed the supercritical wing. NASA developed it to delay the onset of shockwave formation over the wings. When air travels over a wing, the air on top accelerates. This means that even though the plane itself might be traveling below the speed of sound, the air over the wing may break it and create a shockwave. This shockwave decreases lift and causes an increase in drag. This kind of drag is called wave drag, and planes need to fly below the speed this occurs at. The speed is called the critical Mach number. The supercritical wing was designed to increase the critical Mach number. The flat top of the supercritical wing means the air does not accelerate as much as it would over a classic aerofoil. Of course, this causes a loss in lift because that fast-moving air is causing a drop in pressure on top of the wing. To compensate, supercritical aerofoils have this concave curvature underneath the wing, which causes an increase of pressure there to compensate. This increase in pressure does not affect the critical Mach number, while the larger radius of the leading edge increases the lift generated at higher angles of attack. This is because air struggles to follow the tighter turns of a smaller radius leading edge, which causes earlier flow detachment and stall. The larger radius delays this flow separation. This aerofoil shape changes continually as you travel the length of the wing, twisting and curving in computer-calculated precision, optimizing the wing shape to be as efficient as possible, and Composites provided the engineers with the confidence that these shapes could be manufactured. The skin is simply laid down on a mold with automated tape laying once again. We don't have to beat metal into shape each and every time we want to recreate these delicate curves. The fibers of the wing have even been laid in specific patterns to tailor the stiffness of the wing in different areas. This means the wing deforms exactly as the 787's engineers wanted to as it gains speed. So, the wing shape actually changes during flight to better suit the needs at different speeds. This is called aeroelastic tailoring and is the forefront of state-of-the-art aeronautical engineering today. The 787 also features a novel device designed to reduce turbulent flow over the tail of the aircraft. Two types of flow states exist in aerodynamics. Laminar flow occurs at low velocities and is characterized by fluid layers flowing smoothly over each other in neat, orderly layers. Laminar flow is predictable and non-erratic and does not create significant drag. Turbulent flow is far more common, but still very little is known about how to predict its behavior. It is very difficult to control because of the formation of small vortices called eddies in the flow, making the flow highly erratic. Turbulent flow occurs at higher flow velocities and causes a significant increase in drag. At cruising speeds of 80 to 85% of the speed of sound, turbulent flow is ultimately unavoidable, but we can work to minimize it. Boeing has developed a technology that helps them delay and control the formation of turbulent flow called hybrid laminar flow control. Details on their implementation of the technology are sparse. This technology is capable of reducing fuel burn by as much as 30%, and so companies are keeping their research extremely secretive to keep their competitive advantage. Here's what we know. In the late 80s and early 90s, NASA and Boeing began investigating a suction system on the 757 that would draw in boundary layer air, that is, the layer of very slow-moving air that clings to the surface of moving objects. The outside skin was permeable to air through tiny perforations, too small for the naked eye to see. Manufacturing the permeable surface while also keeping the tiny holes clear of debris is one of the many challenges with this technology. The outer and inner skin were then attached to an elaborate plumbing system that was connected to a turbopump, which sucked air from the boundary layer of air that would form along the plane's surface. By doing this, they could drastically delay and reduce the size of the turbulent flow, and in turn, reduce the drag on the plane. There is no space for this ducting system inside the wings of the 787, but from what we do know, it is inside both the horizontal and vertical tails. However, the only clue of their presence are these tiny doors, whose purpose are a mystery to me with little to no information available online, a testament of how advanced this plane is. Composites give plenty of advantages, but it does come with some disadvantages. When we examine the plane's composition, one material jumps out at me. 15% of this plane is titanium. That's much higher than normal. Titanium is an expensive material, so they must have had a good reason to use it over aluminium. Aluminium is typically corrosion resistant when it's left on its own, but when it is placed in direct contact with carbon fiber composites, something strange happens. The aluminium begins to corrode incredibly quickly. Something about carbon fiber causes aluminium to oxidize and fall apart. Carbon fiber is like aluminium's kryptonite. This phenomenon is called galvanic corrosion, and it happens when two materials that have dissimilar electric potentials or nobilities are placed in contact with an electrolyte, like salt water. If we look at the Galvanic series, which quantifies materials' nobilities, we can see that graphite is very noble, on the far end of the left scale, while aluminium is quite far to the right. When this occurs, an electric potential forms between the two materials that causes the two materials to trade electrons and ions, which results in the anode being eaten away. This effect is made even worse when the surface of the more noble material, the cathode, is very large in comparison to the less noble material, the anode. Say, for example, when carbon fiber composites are fastened together using aluminium fasteners. To avoid this corrosion, the engineers needed to pick a material closer to carbon in the Galvanic series, and the closest suitable metal was titanium. This has been a huge source of cost in manufacturing. Boeing's production cost was higher than its sales price for quite some time, meaning they were making a loss on each aircraft sold. This is fairly typical for new airliners, as R&D and manufacturing tooling costs take time to recoup, and companies like Boeing typically spread these costs over a period of time on each plane, instead of just having a massive negative balance sheet in 1 year. But because the 787 was so radically new, these sunk development costs, called deferred costs, were expected to reach $25 billion before Boeing even reached a break-even point on each plane sold, where the cost of manufacturing equaled the sales price. In comparison, the Boeing 777 reached $3.7 billion. To recoup costs as fast as possible, it was essential that Boeing reduced the cost of production, and high on their list was the elimination of titanium parts where possible. The frame around the cockpit windows, for example, were initially made out of titanium, but were changed to aluminium with a special coating to prevent corrosion, while some parts that were originally titanium were changed to composites, like the door frames. Other improvements were sought to make the manufacturing process for titanium less costly. Many metallic parts used on aircraft start off as large blocks of metal that have to be machined down into their final shape. This results in a ton of wasted metal as the metal is gradually shaved away. Aircraft manufacturers quantify this wastage with something called a buy-to-fly ratio, and it's a huge source of increased manufacturing costs. Costs that Boeing has tackled by collaborating with Norsk Titanium, a titanium 3D printing company. Now, making 3D printed metal parts is not easy. Most titanium 3D printing involves a powdered titanium that is melted together using lasers. Researchers used high-speed X-ray imaging to visualize what happens during this process and found a lot of imperfections. The track varies in height, the powder gets blasted away, resulting in varying thickness and separated tracks, and even bubbles form, causing pores in the metal. This creates parts with a lot of micro imperfections, and imperfections lead to decreased life as fatigue causes cracks to form. We can visualize a material's fatigue strength by plotting on an SN curve, which places the magnitude of the alternating stress on the y-axis and the number of cycles it survived on the x-axis. For traditional machined titanium, it looks something like this, whereas for 3D printed parts, it looks like this. 3D printed parts simply fail much sooner because of these tiny imperfections. Norsk has worked to improve this. Instead of using laser sintering with powder, Norsk have developed a revolutionizing, patented, wire-based metallic 3D printing system for titanium that they monitor with 600 frames per second cameras for quality control. These 3D printed parts are then machined down into their final shape, reducing the total titanium used by 25 to 50%, and their printing method is 50 to 100 times faster than the powder printing method. This process resulted in the first ever FAA certified 3D printed structural components, and they first flew in the Boeing 787. This plane is truly innovative. Titanium was not the only material Boeing worked on removing from the plane's construction to save on cost. Copper once formed an important part of the 787's wing, where it was laid down in thin strips on the wing's surface. This is not a typical design choice for aircraft wings, and once again, it was influenced by the 787's composite construction, because composite materials are not good conductors. Carbon fibers are great conductors, but problems arise because of the plastic resin binding them together, as this resin is an insulating material, preventing the passage of electricity, which is a massive problem for planes as getting hit by lightning is not a rare occurrence. One study calculated that lightning strikes occurred once every 3,000 hours of flying between 1950 and 1975. A 787 was struck by lightning while taking off from Heathrow. Upon landing in India, 42 to 46 holes were found in the fuselage as a result of resistive heating. The plane survived and was flown back to London for repairs with no passengers aboard, but Composite's vulnerability to this kind of damage is a drawback, and the repair process is more complicated than with aluminium. However, this strike could have been much worse. If the electricity does not run smoothly along the surface of the plane and exit, it may cause a spark in the fuel tanks and cause an explosion. This kind of accident was not uncommon in the early days of the airline industry. Pan Am Flight 214 was struck by lightning while it flew in a holding pattern, waiting for a lightning storm to pass at Philadelphia International Airport in 1967. Its left-wing fuel tank exploded, causing the plane to barrel out of control to the ground in flames. Since then, the aviation sector has implemented rigorous safety measures and lightning protection tests to ensure an accident like this could never happen again. Early 787 wings were designed with copper strips to ensure the electrons had a path of low resistance along the surface of the wing, ensuring they wouldn't travel to the fuel tank and cause a spark, while also preventing resistive heating damage to the composite structure. Fasteners were sealed with an insulating material to stop electricity from traveling down the metallic fastener into the fuel tank, and the fastener themselves were fitted with compression rings and a sealant to eliminate potential spark locations caused by gaps and sharp edges. Finally, the 787 has a nitrogen inerting system that fills the tank with nitrogen. Ignition can't happen without oxygen. Boeing has since removed 2 of these protections in a challenge and required a complete redesign of several systems and an entirely new engine.